Chapter 6, SOHCAHTOA. Basically, what we're going to be looking at in this section is a right angle triangle. Typically, you call this angle here, let's call it theta. And then we name the sides according to opposite, adjacent, and hypotenuse. This fellow is called opposite. This fellow is the adjacent. And this fellow here is called the hypotenuse. And what SOHCAHTOA does is it allows us to find, using the sides of a right angle triangle, the exact value for a sine, cosine, or tangent of any given angle. So if I told you that this was 7 and this was 2, and I asked what was the size of angle theta, and you could get a question just like this, a pretty straightforward one, where you're told two numbers and you're being asked to find an angle, you would look at this and say, okay, opposite, adjacent, which one of the three SOHCAHTOAs use opposite and adjacent?
Opposite adjacent is tan.
Correct. So you would write down tangent of theta is opposite over adjacent, and that would be 7/2. And to get theta then, you would just do the inverse tan of 7/2. And I'm assuming that the question is in degrees. And so I'm doing inverse tan, although you can't see me doing, I am. And I'm going 7 divided by 2, and I come up with the answer. Let's say they want the answer to 1 decimal place. Then the answer would be 74.1 degree. Now, it's a pretty standard, here's a right angle triangle, here is some information, in this case 2 sides, find a missing angle. Now, once you know this angle, can't you also find this angle up here, almost for free? Great. So you might get a question where you have to find everything that's missing. You'd still start by finding this angle. Then once you found it was 74.1, wouldn't you then be able to figure out, well, what's left? Well, there's 15.9 left, so that's what would go there. And how would you find the missing hypotenuse?
A squared plus b squared equals.
Right.
Oh.
Yeah, you're right. Right, Pythagoras?
Yes.
The easiest way to do it. That's 49 and that's 4, so whatever the square root of 53 is, although square root of 53 would be fine, it's an exact value. And if you've done anything on the homework, I'm sure you've all came across the rather frustrating at times feature that that the software isn't very clever at identifying different versions of the right answer. So for instance, the square root of 53 is correct. And if I find it as a decimal, the square root of 53 is about 7.3. Now, if the question says find the exact value, then you must write down the square root of 53. If it says give the answer to 1 decimal place, then you write down 7.3. So you have to be aware how they phrase the question so that you can be sure that you're writing down what it was. And sometimes, if there's more than one step to the question and you did a bit of rounding off, your answer might be just a tiny bit different from theirs, but enough different for them to give you a wrong, which is why showing me your working is so important. Why sending it to me, because I can look at it and I can figure out that you were fine. They were just being a bit nitpicky about it. So that would be one example of SOHCAHTOA. There is a number of features. I'm trying to think of some cool stuff that we could do. Oh, they always like to throw in some story or other involving walls and ladders and looking at tops of mountains and so on, some kind of application question. So let's suppose that you had this building, very strange building because it's skinny, and that you were 50 feet away from it, and the angle of elevation to the top was 31 degrees. And the question would then be asking you to find the height of the building. Now, you might or might not get a picture. Sometimes the WebAssign gives you a little picture of it. Sometimes they just give you it as a sentence. So imagine this question was, person wanted to find the height of a building. They walked 50 feet away from the base of that building, and the angle of elevation to the top was 31 degrees. How high is that building to the nearest foot? Right, that's probably the way it would be phrased. Okay, with this type of question, how are you going to approach it? What would be your first step?
Identify like what you need, like what the right SOHCAHTOA thing.
Okay.
Yeah, does that make sense?
Yes, it does. So can you imagine that's the right angle? And so to identify which of the three SOHCAHTOA formula you're going to be using in at least this question, we have to identify, from this angle's perspective, the names of the sides that are going to be important. And the sides that are important in these puzzles are ones that you know the size of, or ones that you're trying to find the size of. So in this case, this side here is called opposite, and this side here is called adjacent. Now that you've identified the sides, you can then figure out which of the SOHCAHTOA fellas we're going to use. So I need to find an opposite adjacent combination again, right?
Yeah.
But in this case, the tangent of 31 degrees is going to be the opposite over the adjacent, which is fine. The tangent of 31 degrees is going to be the opposite, which is basically the height that we're trying to find, divided by 50 feet. And now we have to figure out how we're going to find the missing height. Almost every one of these SOHCAHTOA questions will look like this. You put in a little over 1, and the reason I do that is because what's going to happen next? Can you see what's going to happen next?
Gonna multiply each other, cross.
Right, cross multiply. So the height times 1 gets you that, and 50 times the tan of 31 gives you that, and 50 times the tangent of 31 is roughly 30 feet. It's actually 30.02 feet, but 30 feet will do. Now, you can't see me doing this, but I'm going to do something. And I'm going to do a different calculation. Well, the same calculation, but with a different answer. And I wonder if you can figure out what went wrong. I went and did a different, I did this same calculation with a little change, and the answer I get is negative 22 feet. What on earth happened? I went and typed in 50 times the tan of 31, if you want to see it, if you can.
Did you put the negative, the inverse tan?
No, that could have been a mistake, but not this time. Do you see it's 50 times tan 31?
You made it radians or something?
Yes, I didn't mean to make it radians, but have you noticed that if you don't pay careful attention to your calculator, can't the radian degree thing catch out? Now in this case here, I think you already would have said to yourself, come on, negative 22 feet, that doesn't make sense. I wonder what I did wrong. But in some circumstances, the number doesn't look particularly weird. It's still wrong, right? It's, you know, whatever it is, it's still wrong, but you won't notice it. So try and remember, I would probably do that. The first thing I'm going to do whenever I do my trig exam is I make sure it's in degrees. And then whenever I reach a question where things have to be done in radians, then I change it to radians, I do whatever it is, and then I go back to degrees. So I always know that my default position is degrees, and I must change it if it's not degrees. And that way it's a way of keeping me focused. Otherwise, if you forget, you know, if you keep jumping between one and the other all the time, sometimes you'll forget that you haven't switched it back. Right? You'll think, yeah, I'm okay, it was good for the last question. This one's 22 radians or whatever. You won't notice it. So you can get missing sides, you can get puzzles. Let me kick out of this for a few seconds. We can. I'm going to go in. Is there any part of chapter 6 that in particular you would like me to go over? Any topic within the right angle triangles?
Oh, not that, but something else.
Oh, well, we can.
Well, it's the one with the radians, whatever. The one with the, what's like the circumference or something? I don't know.
Oh yeah, yeah.
You know what I'm talking about?
I do know what you're talking about, right? But that's not in this section, so we'll keep that till
Really?
another day.
Really?
Yeah. The triangle? Oh, wait a minute.
I thought that was section.
Oh, you're right. You're right. I take that back. Take that back. Okay, well then that's what we shall do.
It's like the one with the W or whatever. I don't even remember.
Well, I'm not sure what that is, but if it's what I think it is, the kinds of questions sounds like you're talking about.
There's like time had to do with the time it takes for, I don't even remember anymore.
I do. Here we go. There's a bicycle, right? I don't know if you can see it yet, so I'm going to put it on screen so you can see it. And we're going to do one of those bicycle stories, right? So the diameter. What's a good diameter for a bicycle in feet? How big's a bike?
2 feet? I don't know.
2 feet? 2 feet.
Oh, diameter?
Yes, 4 feet.
I don't ride bikes.
4 feet it is then, right? That's either a clown bike or whatever, but it's a 4 feet diameter, right? And this is going to be the how fast is the bike going in miles per hour, right? So we've got, is that the question you're talking about?
Yeah.
Okay, so now we've got this puzzle about bicycle wheels, and we're being asked the speed in miles per hour. Okay, so what I got to figure out here is what else they would tell you. Well, not only would they tell me the diameter, they would tell you that this person can cycle with 20 revolutions per minute. So they're not going very fast, right? 20 revolutions. The wheel will turn 20 times in a minute, right? Roughly every 3 seconds, the wheel turns round. So you can imagine 101, 102, 103. This is casual biking, right? Now, if I made that 200 revolutions per minute, it would be the Olympic speed bikers, right? But the number's not important, it's the process, right? So this bicycle wheel, this person is riding his bicycle. He goes with 20 revolutions per minute. The diameter of the wheels are 4 feet. Find his speed in miles per hour. So that's the storyline built up. So first I'm going to do is I'm going to get the circumference of that whale. And that's going to be pi times 20, which is what? 20 pi, right? And the units are still in feet, right? So in one turn, 20 feet. That's actually quite a big wheel then. Second, in 20 revolutions per minute, you will get 20 times this guy. So that's 400 pi feet per minute.
Did the circumference be pi times 4, or why is it pi times 20?
The circumference is pi times diameter. It's always been that.
Diameter is 4 feet.
So what did I do? Ah! Did you all catch that deliberate mistake? I think my brain was thinking of that. Whatever. We're all caught. So 80 pi feet per minute. Okay, let's figure out what that is as a decimal. I'm going to have to bite the bullet sometime. So 80 times pi is 251.3. Now what we're doing next is we're going to convert that into miles per hour. Okay, so if you do that many feet in a minute, if you multiply this number by 60, isn't that how many feet per hour? So we've got one of the units up to the value you want. So 251.3 times 60. Let's try that again. 251.3 times 60. I get 15078 feet per hour, which is what? 15,078 feet. Okay, almost there. How many feet are there in a mile?
Not like 5,020.
280.
80.
So if you divide this by 5,280, you will get the answer in how many miles per hour. So here it goes. 15,078 divided by 5,280, and we are looking at approximately 2.9 miles per hour. So it was a very leisurely cycle. Are we cool?
Yes.
Right. Okay, let's move on then and do sine rule, cosine rule. Sine rule and cosine rule are only used, or really should only be used, in triangles that are not right angled. If a triangle is right angled, SOHCAHTOA is the guy to go to, right? He's the one that you can use, gets you the answers the best. So let's look at the sine rule first. Call this guy capital A, capital B, capital C. And then you name the sides little a, little b, little c. Are you comfortable about how to name a non-right angled triangle? The angles at the corners are capital letters, A, B, and C in this case. And the sides are little a, little b, and c. And little a is opposite A, little c is opposite C, and little b is opposite B. And then you have You have that relationship. Now, as long as you give me enough information about this particular triangle, you should be able to find any angle or side that's not given. So as long as I give you particular kinds of information. So in this case here, let's suppose that I tell you that this angle up here is 80 degrees and that this side here is 7. And I tell you this angle here is 30 degrees. Now, in this kind of question, really what you're being asked to do might be to find little a, or to find little c, or to find angle c, right? You could be asked to find who this guy here is a, who this little guy over here is c, or who this angle over here, capital C is. Right? Now, in some of the situations, you don't need the sign rule. You can actually do it much quicker than that. Suppose I wanted to know angle C. How would I get it?
Like add them all together. Like subtract 180 minus the two angles.
Yeah. So Tyler, you'd add 80 and 30 and you take it away and you get 70. Seems reasonable?
Yeah, 70.
Yeah, everybody agreed. So I guess I'll put 70 in. So let's pretend that this question had been find the size little c, right? Just one side of the triangle, the little c side. So you check off angles that you know, and you also check off sides that you know, or sides that you're trying to find. So do you see in this particular world, those two guys are the ones that I would use. So I'm going to do sine b over little b is sine c over little c. Angle b is 80 degrees. Little b is 70 degrees over little c. And you typically end up with two fractions where one of the three numbers is missing, right? In this case, the little c is missing, right? The way that you solve them is pretty much the same each time. Can you see that we're going to be doing a cross multiplication first? And the cross multiplication, these two, c sine of 80 degrees equals 7 times the sine of 70 degrees. And then to get little c, you divide both sides by the sine of 80. If you can, most situations you should be able to do this. Do you notice that I didn't turn anybody into decimals yet? I kept them just the way they are, right? Sine of 70, I just left it as a sine of 70. And at this point here, I can then use my calculator. And so I'm making sure that I'm in degrees. Easy mistake. And I'm going to go 7 times the sine of 70. And then I'm going to divide that by the sine of 80. And the answer I get, let's say they want the answer to one decimal place, is 6.7. That's a standard sine rule question. Now, if you look back at what we did a few minutes ago, and didn't I ask you to find, or asked you what side angle C was? And then after that, I asked you for little c. Do you know what they might do is they might ask you just to find little c. And that means that you would have to realize that you'd have to get angle C first before you could even find little c. So when you've got one of these triangles, whether it's the sine rule or the cosine rule, it doesn't matter. Will you look at all the information that you've got and then see if there's anything else, like another angle that you can get for free, and get that angle as well, because the chances are you're probably going to need it later on anyway. So even if they don't specifically ask for angle big C, in this example here, you needed to know it before you could actually do it. Otherwise, you would have a picture that looks something like this. You see all the check marks don't match up. The middle two are good, but you see the A only has a check mark at the top and nothing below it, and the C only has a check mark at the bottom and nothing above it. You see, in that case here, you'd be kind of stuck if you didn't realize that you needed to get angle C as well to be able to complete the process. Now, if you do the classic cosine question, actually, I'll keep that one there for a comparison. And when you do a cosine question, the triangles get named the same way. So we'll just call this A, B, and C again. In this case, I'm going to make this 40 degrees. And get my little naming thing going here. There's a little A, there's a little B, there's a little C. And let's make this guy 30 and make this guy 10. Now this is going to be find. Hey.
Okay, I have a question.
Yes.
Isn't there like that one rule in like the sine rule where you can have like another triangle or whatever?
You can, but that will only be when you're looking for a missing angle. So after I finish this question, I'll see if I can put that in as my last example then.
Okay.
So let's get this guy on the road. When I look at this question, how do I know that I'm going to be using the cosine rule and not the sine rule? What is it about this information that tells you it's a cosine rule question?
None of them.
Like,
right, someone else? What was that?
you have a side angle side.
Yeah. So if you ever have side, angle, side, side, angle, side, right? Two sides and the angle in between. And the second combination that the cosine rule has to be used for is side, side, side. That's when you know all three sides and you try to find an angle, right? So if it's two sides and the angle in between that you're given, cosine rule. If it's three sides and that's all you're given, it's a cosine rule. Everything else, sine rule. Right, now in this fella here, we've got angle A, we know little b, we know little c, and we're trying to find little a. The formula is a squared equals b squared plus c squared. Take away 2bc cosine of a. And so we've got 30 squared, add 10 squared, take away 2 times 30 times 10 times the cosine of 40 degrees. Now, although there's a lot going on there, it's not that hard to do because it's really just chug. So I'm going 30 squared, I'm adding 10 squared, I'm subtracting 2 times 30 times 10 times the cosine of 40. And I'm looking at the answer 540.4 roughly. Is that what I was asked to find? You're shaking your head, correct, Tyler? It's not, is it? What have I been asked to find? The answer that you type in the box is not 540.
Don't you need a square or something?
Yes, you do. Now, if I take the square root of that guy, it's 540.4, and the answer I get He's a much more realistic, that fella. So look at your question and look at, in particular, your picture. Always draw pictures. Now, if I put this picture and I look at the answer 540, would you agree that it just looks far too big to be that missing side? I mean, it just doesn't make sense, right? And so that might be a warning signal. Oh, yeah, I've not found A yet. I've only found A squared. Does 23 and a bit look much more reasonable in that picture, right? So the size of your answer should reflect the circumstances in the triangle. Right, now, if this triangle was 1 and this was 3, can you imagine these are small numbers? That was 1 unit long and that was 3 units long. If I thought the third side was 23.2 units long, physically, isn't that stupid? How can you have a 1 and a 3 and still get 23 between them? And the worst it could be is like that, and that only adds up to 4, right? So look at your answer and say, in the context of my picture, does that seem to be a reasonable size? Now, moving on to our last situation for today then, and that is going to be a question where you've been asked to find a missing angle, and there might or might not be 2 answers to it, right? So here's my triangle. I'm going to make one up, hopefully. I'll make this angle here 5 degrees. I'll make this 10. Call that A, call that B, call that C. Now I've got to figure out how to make this happen. Okay, I'm going to go 7. And see how this one works out. So in this question, we're being asked to find angle C. So if I do my sine A over A, sine B over B, and sine C over C, and I start checking things off, well, I know angle A, I'm trying to find angle C, I know little c, and I know little a. So it's A and C is going to be the combination. And I know of the sine of 5 degrees over 10 is the sine of C over 7. Now, I made this question up. If this doesn't work, in other words, if I get an answer that's impossible, I will change the question, right? But I'm hoping that I don't need to do that. Okay, here goes. I'm pretty sure actually I'm safe. What's my next line of working going to look like?
Cross multiplication.
Okay, so 10 times the sine of C is going to be 7 times the sine of 5 degrees, which makes sine of C 7 times sine of 5 degrees, all divided by 10. And I'm going to find out what that is now. So it's going to be 7 times the sine of 5 divided by 10. And I get 0.061. Okay, how do I find angle C now? It's the only thing that's left.
Inverse.
Okay, so I'm going inverse sine of 0.061. That should be accurate enough. And I get 3.5 degrees. And that is correct. Angle C being 3.5 degrees is a correct answer. Or What would the other possible angle be? Well, you need to find another angle whose sine is equal to this. The one that we've just found is that guy there. The other one that might work is the second quadrant, because over there's an angle that will have the same answer in that, and that makes a base angle of 3.5. So the other angle could be 176.5 degrees. Now, whenever you find a missing angle in the sine rule, there will be two answers. There will be this one, which is guaranteed to work, and or another one that might work. So let's look at context here. This second possible answer is 176 and a bit. That angle can't change. Can you fit 176 here, or I should say here? Can you fit that guy with an angle of size 176? Yes or no?
No.
No. So in this case, only one answer. Can you pretend for a minute that this angle wasn't 3.5, but 30 degrees, something nice, or 35 degrees, right? Can you pretend for a minute that in a different world with slightly different numbers, I got that the correct angle that we could use was 35? Then in that case, wouldn't the other one be 145 degrees? Right? Can 145 fit this picture? Yes, it can, right? 5 and 145, they can work. They add up to 150. So that would get me, well, the other angle. I keep pointing at the top, but I mean C. So when you're looking at finding missing angles from the sine rule only, there may well be two choices. There's the one you get, which is good, and then the other one is what's left when you take it away from 180. That second one may or may not be usable. In the example we did, it wasn't. But can you imagine in another situation there might be two correct answers?
So when do you use that rule?
You will use what? The rule about finding two possible answers?
Yeah.
You will always use it.
Oh, okay.
You will always use it when you're looking for a missing angle.
Only for a missing angle? Okay.
Right, because when you do a side, you don't get this issue.
Okay.
Right, when you're looking for a missing side, there's just the number that you get. That's the only answer, right? But when you're looking for a missing angle, there are two alternates. It's okay with the cosine rule. You don't worry about it in the cosine rule. The cosine rule, the angle you get is the only angle that's possible. There's not another angle you need to look for. So cosine rule, one answer, forget about it. Sine rule, when you're looking for an angle, there will be two possible answers.
So,
one is guaranteed, the one you get, right? And the other one might or might not work.
So one more question. Do you can you use the sine rule and after you're finished with if you're using the rule of cosine to check your work or something?
Sure, why not? Do you know some of those questions that are big ones, we didn't have time to do that today, but in some questions you use the sine rule to get this, and then you might use the cosine rule afterwards to get that. More likely you'll use a cosine rule maybe to find an angle, and then you can use the sine rule to find everything else that's missing, something like that as well. Yeah, you can mix and match the two processes. Really, whichever one you think is easiest to deal with should be your go-to guy. Because typically the question just gives you a triangle with some information, and your job is to find whatever angle or side they want you to find.